Second and last tutorial for this lecture by Bram. Thank you very much.
Thank you for the introduction. Okay, so the plan for today is on the blackboard. So I plan to give a very short recap of what we did in the first tutorial, which was related to Dutch representations of story code and its strange correlators. And then, as a second example today, I want to talk about the derivation of perhaps representations of more general string nets, of type and when models. And I will take Fibonacci as an example to that. It has most of the subtleties, most of the machinery involved in derivation. That was also presented by Lootens in his lectures. And then, as an application of that, I will also consider a strange correlator of that model, which will be the hard hexagon model. And so the hard hexagon model, I will introduce it in the last part of my lecture, my tutorial. And so this is a model of hardcore bosons or hardcore molecules on hexagonal lattice. It's a very, well, you could say it's a very realistic model of molecules on a lattice. And it's a very nice example of something which has non-invertible symmetries given by Fibonacci fusion category. Okay, so as a recap, what we did the last time out was we looked at story codes, or in different jargon, the string net with VecC2 as fusion categorical input. And so what we did was we constructed two ground state representations of that model. And so to connect back to what Lawrence was talking about in his lectures, is that we can understand those two different representations as different choices of module category over VecC2. So just to rephrase the result that we got in that language, I can use a theorem that classifies module categories over groups, over VecG if you wish. And so the theorem says that module categories over VecG, where G is a finite group, abelian or non-abelian, doesn't matter, are given by, or are in one-to-one correspondence with subgroups and two cocycles on that subgroup. And so Lawrence talked about module categories over RepG. Those are also classified by the same piece of data, which is not coincidence exactly because of Morita equivalence that was also mentioned in the lectures. And so for VecC2, we have two choices. We have one choice corresponding to Z2 itself. There are no two cocycles involved in this example because Z2 doesn't have a non-trivial two cocycle. And this corresponds to module category R, which we call Vec. This is the module category, which is the category of finite dimensional complex vector spaces. And then we also have trivial subgroup, which corresponds to R equal to VecC2 itself. You can always choose as module category the fusion category itself. And those correspond to the two ground states that we derived. And if I remember correctly, this ground state corresponds to the first ground state that we derived in that lecture. So ground state 1 from that lecture corresponds to this choice. And then the second one corresponds to ground state 2. Okay. Just to put things a bit into perspective. And then as a second step, what we did was we took the overlap of these ground states with product states, which we called beta. And we interpreted this entire thing as a partition function, so it's a number and we interpret that number as a partition function of a certain stat-mech model. And by fine-tuning this this product state, this ansatz of this product state, we could obtain the classical two-dimensional Ising model from that. And then we showed, or we argued at the very end, that by toggling between different ground state representations and keeping this product state fixed, that we could actually implement Kragh-Vancraeynest duality on the lattice in this stuff. And so by changing R while keeping beta fixed, we had the Kragh-Vancraeynest duality of the Ising model. Okay. So that's a bit of recap of what we did last time.
Sorry, can I just make a comment on the theorem, just to be a bit pedantic?
Mm-hmm.
There's an equivalence relation on this data, yeah. So up to subgroups up to conjugation, subgroups and two co-cycles up to conjugacy.
Yeah.
Yeah,
exactly.
and the co-cycles are labelled by like in H2 in cohomology, not just closed, but up to cohomologies as well.
Thanks.
Okay.
Okay, so the second part will be about the Fibonacci string now. So let me just first also introduce some graphical notation for the string diagrams that we will be using throughout this lecture. So part 2. Conventions. So these are conventions for the string diagrams that we will be writing down for unitary fusion categories. Without multiplicity. If you have multiplicities in the fusion rules, then you can just repeat the story I will tell today without much difference, and you will also be able to just write down perhaps representations of ground states of Levin-Wen models with input categories with multiplicities. And so the conventions that I will be using are mainly normalization conventions. So I have some resolution of the identity on the objects of my fusion category D, which is as follows. So in everything I will draw right now, A, B, C, D, E, F are assumed to be simple objects of my fusion category. I also have the ability to remove bubbles in the following way. And then my F symbol is written like as follows. And then using all of these diagrammatical conventions and manipulations, we can also, for example, look at the following diagram, which I will be encountering a couple of times in this lecture. We can, for example, encounter trivalent vertex, but where the vertex is sort of inflated in the following way. So all of these lines are again labeled by simple objects. And I will try to get my conventions right for the first try. A, E, and D label the lines in bubble. And then the outer lines were labeled by B, C, and F. And then using one F move and then the rightmost identity, so the bubble pop identity if you wish, I can write this as an F, A, B, C, D. That's why I chose the labels as I chose them. E, F. And then a bunch of quantum dimensions. C and B. Okay. I will not derive this, but it's something that you can very easily derive yourself by just recognizing a fusion tree within this diagram, applying one F move, exactly this F move, and then there will be a sum. With the sum will be cancelled by the delta that you pick up by applying the bubble pop identity on the top board. Okay. And so I will be applying this to the Fibonacci fusion category. So I will now write down the data for the Fibonacci fusion category. Okay. So it consists of two simple objects, which I will be calling 1, which is a monoidal unit. So tensouring with 1 gives the object itself. And then there's a non-trivial object tau. The fusion rules are then given by, well, there's only one non-trivial fusion rule, which is given by tau squared is equal to 1 plus tau. Okay. And then from the fusion rules, you can just directly infer what the quantum dimensions have to be, because the quantum dimensions are the unique positive solution, or the unique positive solution to this equation. So they sort of form a one-dimensional representation of the fusion rules themselves, and then you can infer that the quantum dimension of the identity is, of course, 1. The quantum dimension of tau is equal to phi, where phi is a positive root of polynomial equation phi squared equals phi plus 1. And so in particular, phi is just equal to 1 to the square root of phi divided, which is the golden ratio. And so the name Fibonacci really comes from the fact that if you take the tensor product of n copies of tau, where n is just an arbitrary integer, that you'd start generating the Fibonacci sequence as the multiplicities of 1 and tau in that tensor product. And then the F symbols. So throughout I will use a convention where the F symbols are just 0 when they are not allowed by the fusion rules. So for example, if I take an F symbol where the labels A, B, and E are not allowed by the fusion rules of my fusion category, I will just say that that F symbol is equal to 0. And so the F symbols of Fibonacci are just equal to 1 or 0, depending on whether all the fusion rules encoded in that F symbols are allowed or not. There's only one non-trivial F symbol, which is given by the following. So F, tau, 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 tau. It's a matrix, and that matrix is given by 1 over phi, 1 minus 1 on the diagonal, and square root of phi on the other diagonal. And this is a unitary matrix, it's self-inverse, and you can just easily check that by using this identity on the phi. And this is the data that we will be using in the next part. Is this visible for everyone? Okay.
That follows from hexagon or pentagon, sorry?
Sorry?
Is the solution for F you found follows from the hexagon?
Yes.
In the gauge where it's 0 or 1, but all the other.
Yeah, so it's in a particular gauge where, well, this matrix is unitary. Yeah, so you have made a gauge choice and writing down the F symbol. so what I want to do now is I want to use the machinery that was explained by Lars in the lecture 2, I think, on how to derive the ground state of the 11-when model with Fibonacci as an input, yes?
Is that dA, dd, and df? Or I'm a bit confused because the external line f appears in the quantum dimensions on the right side as well.
So these quantum dimensions, you mean?
Yes.
And what's the confusion exactly? So dA is this
Yeah,
one.
it's inside the loop, but okay. Maybe it's fine. Sorry.
I think it's correct. Yes, I think it's loud, but it should be, if not. And so, just to give a small recap of how we will write down the ground state of Fibonacci string net. We will start from an empty configuration, in the sense that I will put just the trivial object, so the one object on all the edges of my lattice, which will be the hexagonal lattice in this example. This can be done for any trivalent lattice, but I will choose the hexagonal lattice in this example. And then we'll just apply the ground state projector on every plaquette. And so I will write this down now a bit more explicitly. So I will use notation also where a red line is just equal to a line on my lattice labeled by the identity. So I start from configuration. That looks like this. So I just draw again a patch of my lattice, where all the lines are just labeled by the identity. And so this trivially satisfies fusion rules on every vertex, because 1 times 1 is equal to 1. And then I will just apply the 11-when projector, the ground state projector, on every plaquette. Where this projector, I remind you, is given by sum over all simple objects, call them A, and then a loop labeled by A. With a B vector dA divided by capital D, where capital D is total quantum dimension given by square root of the sum of dimensions squared. So the name of the game is now to start from this configuration and then apply this 11-when projector. And so we will use the local moves that I just written down to pull this on the lattice, because I remind you that the dynamical degrees of freedom live on the edges of my lattice, and then use the F move to resolve all of those junctions I will end up with. And the total wave function of the ground state will be given by a whole bunch of F moves or F symbols and quantum dimensions in a way that I will write down now a bit more schematically. So I will just do in the first step a whole bunch of resolutions of the identity, like on the top left. And so in the first step, I will end up with a huge sum of the following form. There's also a drawing that Lawrence made at some point. And so here I just used the resolution of the identity on these lines that I put on the lattice. And by doing that, you just pick up a whole bunch of quantum dimensions, which I write down schematically like this. And then second step, you can recognize this diagram as a diagram that I wrote down right here. And so you use this everywhere, so you will pick up one F symbol and then a whole other bunch of quantum dimensions on every vertex. So step 2 is this one schematic. And so now we'll try to write down a Pep's representation of this ground state wave function. But I just want to stress at this point that it's almost a tautology that you can write down this PEPS representation of this ground state, because what we will just be doing is we will define a local PEPS tensor, which will live on every vertex, and this local PEPS tensor will just evaluate to the F symbol. The F symbol associated with every of those bubbles that we plopped in the second step. Okay. So I will just write down the answer and then try to convince you that this is the right way to do it. And so the tensor that we will end up with is exactly one of those triple line tensors that Lawrence also introduced and talked about in this lecture. In this case, this will be a triple line tensor where all the labels are just labeled by objects in Fibonacci. Because we choose here the regular modular category Fibonacci over itself in the construction of this ground state. So it's a triple line tensor, and we'll just label all of the edges that stick out. So this will be D, F, A prime, D prime, E prime, E, B, C. And this evaluates to delta A prime, delta E prime, delta D prime, F, A, B, C, D, E, F, quantum dimensions D, A, D, D, T, F. Okay. There are more quantum dimensions, but let me already unpack this definition. So I have a tensor with, well, 3 legs, 1, 2, 3. Every of those legs is composed of 3 two-level systems, because every of those legs can be labeled by either 1 or tau. So it's a two-level system of every of those legs. This tensor has some internal structure which is captured by these delta tensors. So for example, if I take a tau on this leg, then also this leg has to be labeled by tau. And what I mean by that is that if I take this as a tensor, I store it in my computer, then every of those legs will just be a two-dimensional system, and all the components where this entry to my, well, this value that this leg takes is not equal to this one, then I will just put this component equal to 0. So in particular, this is a tensor with, it's a rank 3 tensor with 512, so 8 to the 3 possible entries, but it's very sparse in the sense that only, I don't know, 8 or 10 components of this tensor are non-zero. So that's the internal structure captured by these deltas that I put here. That's also why I'm allowed to just draw this as a straight line. It's just because this value has to be equal to this one, and vice versa for these. And then the F symbol that I've written down here, it's not coincidentally equal to the F symbol that I've written down right there. It's exactly the F symbol that you pick up when you pop the bubble in going from the first step to the second step. And then the quantum dimensions are also the quantum dimensions that you just pick up by doing this bubble pop identity. But there are more quantum dimensions, and it's a bit painstaking to go through the entire computation, but I will just do this for the following application of the hard hexagon model. So there's a whole bunch of quantum dimensions that we missed, because we also have to take into account the quantum dimensions of the resolution of the identity that we apply when pulling the Levin-Wendt projector onto this lattice. So here I missed in the definition of my tensor these quantum dimensions, and I will just choose a convention where I absorb all the quantum dimensions equally in the tensors, in the sense that for every edge I pick up quantum dimensions, and I will just split the quantum dimensions over the vertex terms, the vertices that connect or that touch on that edge. And so the quantum dimensions that I pick up in that way are given by fourth roots of dB, dC, and dF. So these are quantum dimensions of the objects in 3 inner legs. And then I also put the quantum dimensions of the loops. And so, just to remind you, these outer loops, they really come from the objects that are present in the 11-Wen projector. And I pick them up twice every time. I pick them up when applying a resolution to the identity on the edge on top, and on this edge when looking at this this plaquette that resides on this side of the tensor. So I get the dE squared, a dA squared, and a dE squared. And then there's also a whole bunch of quantum dimensions that I get just by looking at these quantum dimensions. So also in the definition of the 11-Wen projector, I have quantum dimensions, and I also have to account for those quantum dimensions. There are some conventions to do this. The convention that I will choose is also, I will just take quantum dimensions from the 11-Wen projectors and just divide them equally over the vertices that are surrounded by this, this particular plaquette. But this requires some knowledge of the lattice that I'm working on, because I just now restrict to the hexagonal lattice. I just know how to divide the quantum dimensions over the vertices of the plaquette, and this will just also give me a whole bunch of quantum dimensions, which are now a 6th root of dA, dd, and dE, which are also just the modules. And I can also simplify this entire expression so these quantum dimensions are given by total 4th root of dB, dC, dF, 1 over square root dE, and then 6th root stays there, 6th roots of dA, dt. Okay. And so this is one tensor that I just derived here. There's another tensor that which resides on well, the other orientation of the vertices. And so the entire BEPS wave function is constructed by taking these tensors, putting them on the vertices of my lattice, and then gluing everything together according to the orientation of the lattice, of the connectivity of the lattice. And then using the contraction convention that I introduced in the first tutorial. So every time I connect two tensors, I will just sum over the energies that are shared between BEPS tensors that are connected. And so a bit more schematically, what the entire BEPS will look like is as follows. Just to make also a bit of connection with the lectures of Lawrence. This is one plaquette. And I have a tensor on every vertex. So for example, this tensor could be this one. It will also be this one. But then I have a rotated version of this tensor on this vertex. For example. So I take all of these tensors, I put them on the vertices. And then, just to be a bit correct and to illustrate how this works in practice, to be a bit more detailed, this is a tensor without physical index. Or I can just interpret this entire thing as a tensor without physical index. But we know that in the 11-Wen model, the physical degrees of freedom live on the edges. So I could also just introduce a sort of delta tensor on the edges to access this middle leg. So I will just do this explicitly for clarity. On every edge, I will introduce a delta tensor that I will introduce just now. And this delta tensor just reads off the middle leg. So if this is A, B, C, A prime, B prime, C prime, E, then this is just equal to 1 whenever A is equal to A prime, B to B prime, C to C prime, and then E is my physical level, or my physical index, which is equal to B, which is the middle leg that runs through. I've already missed some in here. And okay. Yes.
Sorry, I'm getting a bit confused. So you define the ground state with the identity lines and these dotted lines. Step 1 and 2 were simplifications, right? Of that. And then on the top board at the very top, is that a definition of what it means to have the little gap? Or is that
a definition of, sorry, of what?
I'm confused. Is that top equation something that's true in the UFC, or is it something else?
So the top one is a tensor, so it's really an array of numbers.
Right.
It's a rank 3 tensor, and every of those legs, of those 3 legs, is well, 3 copies of a 2-dimensional degree of freedom, which is either 1 or tau. And those really descend from the fact that I have loops on every plaquette that surrounds a vertex, and then the middle legs you have to interpret as the physical degrees of freedom of the lattice, of the model. And so really what I did here was I sketched how to derive the ground states. I told you that in copying every of those bubbles, I pick up one F symbol, and I just now define a tensor that accommodates for this F symbol to evaluate to this F symbol. And so one thing that I also should mention is that because of what I said in the very first part, that this F symbol is only non-zero when all of the fusion rules are fulfilled, whereas otherwise set it's put to 0 when the fusion rules are not satisfied. I also have some constraint on a triple line tensor that every time the 3 legs meet, for example A, F, and D, that those 3 lines have to satisfy the fusion rules. There's also some constraint that's important to have, or to have in the back of your mind. Okay. And so now I want to give a very nice application of this.
I mean, somehow this diagram that you've drawn, I don't know this is what it is, a transistor, I don't know, like this E, A prime, B prime, C prime. It doesn't make very manifest as delta E.
No. Well, I could have drawn something like this. And I could have drawn something which looks more like this. This could have been a better notation. It's very similar to the example of third code that we had. We also had these delta tensors on the edges, which is exactly if you do the computation, if you take these triple line tensors, you put in VexE2, you would really just end up with delta tensor that I also ended up with this in the first line. Okay. And so now what I want to do is I want to take this ground state and I want to construct a straight correlator on top of that. So I will, again, to repeat myself, I will take this ground state, it's a wave function. I will contract it, I will take the overlap with product states. And this entire thing is just a number, but I will interpret this number as a partition function of some model. And I will now try to motivate that the hard hexagon model is a model that comes out very naturally out of this construction. Just by looking a little bit at the fusion rules of Fibonacci. So what's the model? So this is part 3. So the model that we have it's a stop mag model. It lives on hexagonal lattice, of course, but more particular, it lives on the plaquettes of the hexagonal lattice. You can also just define a dual lattice and then define it as to live on the vertices of the dual model, but it's a bit more natural to rephrase it on hexagonal lattice to make a connection with the PEPs that we just derived. So what's a model? So every plaquette can either be occupied or not occupied. So you can think of this as some molecule or some atom that lives on the plaquette. And there's a constraint. There's a constraint that if one plaquette is occupied, for example, this one could be occupied, then the neighboring ones cannot be occupied. Of course, the other right direction, if this is not occupied, then, well, this one can also be not occupied. It's just like a hard constraint that two molecules cannot be on neighboring plaquettes. And so, what's the connection with Fibonacci or with the fusion rules of Fibonacci? If we now identify, and this is something that you can convince yourself is something very natural to do, if I identify the one object of Fibonacci with occupied, and tau with not occupied, then the fusion rules now tell me that if I have, for example, 1 times tau is equal to tau, 1 times 1 is equal to 1, and then tau times tau is equal to 1 plus tau, then I can sort of see the logic of what I just said in these fusion rules. For example, if this plaquette is occupied or is labeled by tau and is not occupied, then the next one is either occupied or not occupied if I put this edge to tau. So if this edge is labeled by tau, then tau times tau can be either 1 or tau. So if this is not occupied, this can be either occupied or not occupied. But if this is labeled by 1, then the next one has to be equal to tau, because 1 times tau is equal to tau. So if this is occupied, then the next one cannot be occupied. The next one cannot be 1. And so this suggests that we can retrieve the hard hexagon model by just taking the PEPs and taking the overlap of product states where all of the edges are just put to tau. And this is exactly what I will do now. So the strange correlator that I want to construct is given by putting tau on all of the edges and taking the overlap with the Fibonacci ground state, the one that I just derived. And just to give a bit more context to this model, so this model is exactly solvable. It was solved in 1980 by Baxter. And the partition function can be expressed as follows. So this is a grand canonical partition function. This can be expressed by following expressions: z to the power n, where z is equal, or small z is equal to the exponential of mu, so the chemical potential times some inverse temperature beta, to the power n, where n is equal to the number of occupied plaquettes. And there is a combinatorial factor g of n, capital N, where g is giving me the number of ways to arrange n particles, n occupied sites on n, capital N plaquettes of my lattice. So the small g is the number of ways to divide n particles and molecules over capital N plaquettes. Of course, with the constraint that two neighboring plaquettes cannot be occupied at the same time. And so the sum runs over n0 to n over 3, because I can have at most capital N over 3 occupied buckets. And so the phase diagram obtained by Baxter is as follows. So a function of z. There will be, for small z, I will have a situation where there are few particles, few molecules, and I will have a very dilute situation. So I have a dilute gas of particles. And then for large z, what the situation will look like is I have a whole lot of particles, and they will try to arrange themselves in sort of closest packet. So just to stare a little bit at the hexagonal lattice, I have some sublattice A, B, and C, and then this one will again be A, B, C, B, and so on. So I have 3 sublattices, and so the particles will try to arrange in a closest packing where either all of the sites on A, B, or C are occupied. And so there will be some competition, so this is sort of ordered phase if you wish. There will be competition between those terms, and at some finite value of Z, critical, there will be a second ordered phase transition, which corresponds to the universality class of 3 state pods. Yes?
How do we control Z from the perspective of the inner product on the right-hand side of the string correlator?
Yeah, a very good question. I will just do this just now in the last couple of minutes.
How does one infer that it's the free-state pods model at the transition point?
So this was obtained by Baxter by just exactly solvable methods. You can construct a strange correlator. You can do some numerics on that. What you can do, for example, you can look at the spectrum of transfer matrix of the partition function just by constructing the PEPs, taking the overlap, and just directly looking at the spectrum of the transfer matrix. And the spectrum of 3 state pods just comes out. You can obtain the central charge with incredible precision just from the PEPs representation of partition function.
And the solution was provided by Baxter?
Yes.
How many minutes you need more?
3.
That's great.
I'll just leave this here. So, what I want to show now in the last couple of minutes is that if I take a strange correlator where I just put all the physical legs, so all the edges to tau, that this model can be identified with partition function of the hard hexagon model. And so what we need for that is we need the exact expressions of all the tensors in this PEPs ground state wave function, where all the physical legs are just projected to tau, and the relevant tensors that you obtain are the following ones. There's one where everything is equal to tau, and I remind you that all of these loops just label whether the site is occupied or not via that identification. And this, if you plug in the F symbol in the quantum dimensions, is equal to -phi -3 for times some constant. The constant is the choice that I have in my choice of a strange correlator. So I can put everything to tau and still weigh that product state with a factor of tau on every edge. And then there's also a vertex of this type. All the middle legs are labeled by tau again. And then there's one loop labeled by 1. There are also rotations. So rotated versions of this tensor where the 1 is on loops. And so here you can very clearly see that if this is occupied, then by diffusion rules on these 3 legs, this side, this plaquette has to be unoccupied, and the same goes for this plaquette. And this, if you evaluate it, is equal to phi to the power 1 over 12 times lambda. So, okay, we can now come to some conclusion. So the partition function can just now be obtained by taking these tensors, contracting everything. And by contracting all of these tensors, you will just count different ways in which all the plaquettes are either occupied or not occupied, with the constraint that 2 neighboring plaquettes cannot be occupied at the same time. Every configuration will be weighted. It will be weighted by a whole bunch of quantum dimensions and this lambda that I will now determine. And so in particular, if you stare at the partition function that I have over there, so the exact partition function of the hard hexagon model, I could look, for example, at the n equals 0 term. That's a term where there's no plaquette occupied, all of them are empty. And this would correspond to a situation where in the partition function, all the tensors are just copies of this tensor. And I want to obtain that term in the partition function is just equal to 1. And so this determines the coefficient lambda. This determines that lambda has to be equal to phi 3 over 4. So that this term becomes equal to phi.
Sorry, why does it have to be 1? That diagram there?
So what I want to do is I want to identify the partition function that comes out of strange correlator with the exact one of Baxter. And I use a normalization condition where the situation where none of the plaquettes are occupied evaluates to 1, because there's like only one way to divide no molecules of all the plaquettes. And so this forces that all of these weights are just equal to 1. And so lambda is equal to 3 over 4. I don't care about the sign because the sign just cancels between different tensors. And so this phi is equal to phi over 6, or the power is 5 over 6. And so now I can just read off what this partition function is, or I can just read off what the fugacity z is of this partition function that I just constructed. Because what I do now is I just take copies of this tensor and I surround it. I surround an occupied plaquette by copies of this tensor. And so an occupied plaquette is the one labeled by 1. And so if I have one occupied plaquette, it means I pick up 6 factors of this, this number. And so if I look, for example, at the situation where there's exactly one occupied plaquette, I can just read of the fugacity of this partition function I just constructed. And the fugacity that comes out is phi to the power 5 over 6 to the power 6, because an occupied plaquette is surrounded by 6 of these vertices, of these vertex tensors. And the fugacity that this corresponds to is 5 to the power 5. And this is also exactly the critical fugacity of the hard hexagon model that Baxter solved. So I think it is pretty amazing that you can just reason a little bit about the fusion rules of Fibonacci, of the hard hexagon model, that you can make a guess of what the partition function should look like as a strange correlator. And this gives you just the critical fugacity by a very simple method of just counting quantum dimensions around those loops. Okay, and so I think that's everything I wanted to say for this tutorial. And so just to recap a little bit, I tried to derive a string net, ground state as a PEPS, to give you some feeling of how to manipulate these tensors, to how to read off of the entries in these tensors and how to play with them a little bit. And I also applied them to the hard hexagon model, which is a very physical model of hardcore molecules on lattice. And something I didn't talk about, but which can be inferred from the lecture of Florence, is that also this model on the virtual level has some MPO symmetries, which are given by the Fibonacci fusion category. And so in particular, this model has, at critical points, some non-invertible symmetry, which is quite extraordinary for such a simple model of molecules on lattice. Thank you.
Thank you very much. not really have time for questions, but if there is a super fast one.
So is there some small deformation that you can do to get tricritical isomers? That would have a smaller central charge and probably also has Fibonacci. And
it also has the Fibonacci symmetry, right? I think so. I should think about this. I think you can just take a superposition of 1 and tau as a strange correlator that gives you tricritical isomer indeed, yes.
So let's thank Bram again and let's